Hello guys, today we're going to be covering section 2.6, which is going to be limits at infinity, horizontal asymptotes. So we learned some more about vertical asymptotes, which are what happen as, as y goes to infinity, or as x approaches a single value. But, we can kind of have a situation similar. Like, I'm sure if you guys remember, we also have horizontal asymptotes. So in this section, we'll let x grow unbounded. So in this case, we're going to let x go to positive or negative infinity and kind of see what happens to y, or what happens to that function. All right. So just a quick example of, a kind of case where this actually happens is just let's consider tangent and inverse tangent functions. So example, let's start with y equals tangent of x, and then y is equal to arctangent of x. So I'm not going to graph the whole plot of tangent. I'm just going to go from negative pi over 2 to pi over 2. And then likewise for arctangent, that's going to go from negative pi over 2 to pi over 2. All right. So if you guys remember about your properties of tangent, is that it has vertical asymptotes at negative pi over 2 and positive pi over 2. This would be your x, y, x, y. So let me just change to a different color. So the graph of tangent of x is going to look kind of like this. It's going to go to positive infinity as you go to pi over 2. It's going to go to negative infinity as you go to negative pi over 2. So if you guys remember that, these inverse functions basically will have these vertical asymptotes. Will basically kind of flip. They'll become horizontal asymptotes. So in the case of arctangent of x, what these vertical asymptotes will become will be these horizontal asymptotes. So as we go to 0 and we go off to as we let x go unbounded or go to infinity, we have that arctangent of x will approach pi over 2. And then the same idea as we go to negative infinity, arctangent of x, those are some crooked ass lines, will go to negative pi over 2. So that's basically the idea of kind of horizontal asymptotes and how we're going to study them. So, as here this will be 5, this could be 100, this could be 10 to the 1,000, add a bunch of zeros. And the fact is that this function will always get closer and closer and closer to the horizontal asymptote. So that's kind of the idea of how we want to talk about our definitions. So what we would say in this case is that the limit as x goes to positive infinity of arctangent of x is equal to pi over 2. And likewise, so the negative side, as x goes to negative infinity of arctangent of x. I spelled arc wrong. Tangent of x is equal to negative pi over 2. So that's basically the notation we would say. That as you let x grow to infinity, arctangent of x will get closer and closer to pi over 2. If we take x to go to negative infinity of arctangent of x, then it gets closer and closer to negative pi over 2. So, this kind of idea is how we talk about vertical asymptotes and how we talk about, infinite limits in this case. What happens as x goes to positive or negative infinity. All right, so now let's do a definition. So let f be some function. Note that this doesn't necessarily have to be continuous. We need it defined to be on some interval going from a to infinity. It doesn't necessarily have a can be kind of arbitrary. It just needs to basically just start somewhere. And if this is true, then we have the limit as x goes to infinity of f of x is equal to L. And this is kind of definitely is very similar to the idea of like limits, of how we normally talk about limits. So prepare for a very similar definition of that. So this means that the values of f of x, can be made arbitrarily close to L by taking x sufficiently large. If I can spell it right. So this idea is that it kind of differs from limits a bit, where instead of x approaching a number, x just never approaches anything. Well, in this case, approaches positive infinity. And sufficiently large just means, let's just say, 10,000 is not good enough. Let's just say we're at x equals 10,000 and we're not as close as we want. Then all that means is that we need to go further down the line. Maybe we need to go to 20,000, and maybe everything after 20,000 will be okay. An idea man, I really should not write and talk at the same time. Alright, sufficiently. Okay. Again, so basically this means we need to let x get bigger and bigger in order for f of x to actually go somewhere. Similarly, what we can do with like the negative version as we go to negative infinity, so let me just say that. Whoops. All right. And likewise, how we said about, a function has to start from a to infinity. In this case, it's going to be a bit backwards. Instead of going, a to infinity, we're going to go from negative infinity to a. Again, a is kind of arbitrary. It doesn't really need to be a specific area. The idea is that you need to start somewhere in order for that function to be defined. And we say, if this is the case, and then likewise as we had above, the limit as x goes to negative infinity of f of x is equal to L. By doing the same thing as above, what that means is that f of x can be made as sufficiently close to L, or f of x can be arbitrarily close to L by taking sufficiently large values of x, well, negative x. Oops, got an email. Okay, so f of x can be made arbitrarily close to L by taking x sufficiently large. So sufficiently, again, just means we need to go, to some really big number, so sufficiently large negative value. In this case, you could just say negative, but the idea is basically the same. Instead of we get to more like 10,000 to 20,000 to 10 billion to 100 trillion, but we're just doing the same thing, but just with negative. So you should note that I'm talking about, positive and negative infinity. So let me just kind of clarify about something before we move on. Let me just write it in red because it's important. So positive infinity, which again, you don't need to write the positive as always, but positive and negative infinity, they're not real numbers. So, and what that means is we can't treat them like that. Whoops. So what this means is that if you like plug in infinity to equation, if you like, try to do some algebra with it, if you're trying to actually plug infinity into a function, that's just whack. So don't ever treat it like it. If you do, I'm going to start a frowny face next to your paper, or comments on it, and I'll be like, please don't. Like, when we talk about real numbers, you can approach infinity, but you'll never get there. But you can always get closer and closer to it. Alright, so let's draw some examples real quick of what horizontal asymptotes will look like. That way, again, it's just not more words. Graphs are sexy. Let's draw some graphs. So this idea of like vertical asymptotes is that you can't really pass over a vertical asymptote nicely, because you just go to positive and negative infinity, but horizontal asymptotes do not have to be like that. So let me mix up the colors. Actually, let me just do this one will be this. 3 different versions. All right. So in this case, we'll say this line right here is y is equal to L. And our function is going to be in red. So an example of like a horizontal asymptote in this case will be like if we have a function that as we get closer as we go to negative infinity, it gets closer and closer to L. And then the function can go like this. It can cross through the horizontal asymptote, bounce back up, and then start approaching the horizontal asymptote again. In both of these cases, and I want to clarify, it doesn't even need to go back up. It doesn't have to approach it from the same place. In both of these cases, the limit as x goes to positive infinity, which I'm just going to leave out the positive sign, of f of x is equal to the limit as x goes to infinity, negative infinity, of f of x is equal to L. So they have the same limit. It doesn't matter if you approach from the bottom or the top. It doesn't matter if you cross over through it. You still have the same limit. So now the thing is that let me try to be consistent, use the same color. The thing is, we don't necessarily need to have just 2 horizontal asymptotes. So let's consider this line, call it y is equal to L. Call this line y is equal to m. M and L are just vague numbers. It could be anything. So one of the things we could do is take this point right here, and this could be like h of x. And we could have a horizontal asymptote that looks like that, where we cross over the horizontal asymptote an infinite number of times. But as we get, even though that we're crossing over, the distance between them keeps on getting smaller and smaller. And this can just go to negative. As we go to negative infinity, that can just go to m. So in this case, though, we have as the limit as x goes to infinity. This is f of x. Sorry. This is h of x. So the limit as x goes to infinity of h of x, that will be equal to just L. And we have the limit as x goes to negative infinity of h of x is equal to m. So again, the thing about, you can have 2 different horizontal asymptotes. You can cross over them as much as you like. The only thing that matters is you just get closer and closer to it. It doesn't matter, it doesn't matter so much that you cross over to it, but basically the idea is that you're always sufficiently close to it. And then one last kind of case. Just do a blue line. Say this line will be y is equal to L. And then our last function will be an exponential function. Oh, well, let's just be in red. But let me, all right. We call this g of x. So in this case right here, we only have we have a horizontal asymptote, but we only approach it from one side. And as you know, as we go in this direction, we go to positive infinity. So in this case, we say the limit as x goes to infinity of g of x is equal to L, and that's it. Well, in this case, you could say the limit as x goes to negative infinity g of x does not exist. So in all the instances above, the limit as x goes to positive and negative infinity actually exist, then that function gets closer and closer to the line y equals L. So basically what this means is if the limit does exist, it's a horizontal asymptote. Or it has to be some line. And that's how we get the definition of horizontal asymptotes. So let's do a definition real quick. We'll say the line y equals L is a horizontal asymptote, or is called a horizontal asymptote, and I might abbreviate this as HA. That way I don't have to always write such big words all the time. So horizontal asymptote. We'll say of y is equal to f of x, because it only makes sense to talk about it in terms with respect to a function. And then if either two cases happen. So either as we go to positive infinity, f of x goes to some L, or the limit as x goes to negative infinity of f of x is equal to L. So basically it just means you approach it from some positive infinity or some negative infinity. So these limits could approach the same value. They could differ, or the limits just may not exist, or one of the limits may not exist. So the only way we need to say that, you know, y equals L is a horizontal asymptote is basically if one of these is true. It doesn't matter what the other one is doing. If we can say yes to one case, then that's good enough. If you guys know about coding, or just means, you know, or just means if something is true, then it says a yes. Hopefully no one who does computer science is going to call me out on my horrible usage of it. All right, so let's keep on going. Let's actually do some, you know, examples. All right, so likewise, we're going to draw another graph. So in this case, we're going to specify a specific function. So it'll be like this. Okay, hopefully it's understood well enough that actually I need to draw it better. So the idea is as x goes to infinity, you know, the line, you know, the function gets closer and closer to the x-axis. In this case, this is the function of 1 over x. We'll say that's equal to f of x. And then likewise, as we go to negative infinity, the function is going to get closer and closer to 0. So basically what's happening with this function is, man, that's a really horrible curve. But basically what's happening with this function is as we go to positive and negative infinity, we keep on dividing by a really big number. If you keep on taking the number 1, keep on dividing it by 10 billion, then you divide it by 100 billion, you divide it by 100 trillion. You get numbers that get closer and closer to 0. So in this case, we would say both the limit as x goes to infinity of f of x, well, not f of x, but 1 over x, is equal to 0, and the limit as x goes to negative infinity of 1 over x is also equal to 0. So we say that y is equal to 0 is an h, is a horizontal asymptote of the function y is equal to 1 over x, or not y so much, but f of x is equal to 1 over x. All right. And that's just a quick example. This kind of works with, well, actually, this works with like x squared. It works with like, well, 1 over x squared. It works with 1 over x to the 5th. And it works with 1 over the cube root of x. So you could check it out. You could try a bunch of numbers similar to this in Desmos. But the idea is it's pretty nice. We get some ideas from that. We do have a theorem we can say about all these cases. Because even if this was like x cubed, x to the 5th, all these graphs will still behave the same. And we still have the same kind of behavior. It's very nice. So let me do a theorem now. Let me mark it in red because theorems are important. All right. Theorem. So say if r is a rational number greater than 0, just in case you guys don't necessarily remember what a rational number is, a rational number of the form is p over q, where like p and q are integers. So basically it's just of the form like, I'm going to go from like 0, 1, like 2, 3, and so on. And this would be like -1, -2, and so on. And obviously q can't equal 0, otherwise it doesn't make any sense. So if this is true, if we have r as a rational number, then we have the following limit. So we have the limit as x goes to infinity of 1 over x to the r is equal to 0. And likewise, we can do this kind of again. If r is some rational number, it is a rational number such that x to the r is defined for all x then we have the following limit. And what that means is that, an example of a rational number would be 1/2. Obviously, if we do like x to the r as like, the square root of x, obviously it's not defined everywhere. So in this case, to 1/2 would be excluded. So we have the limit as x goes to -infinity of 1 over x to the r is also equal to 0. So this is basically saying is that whenever we have a function of this form and r is nice enough, then like regardless of what r is, the positive as x goes from positive infinity it will equal to 0, and the other side of that is if x is defined everywhere for these functions, for an r value, then the limit as x goes to -infinity of 1 over x to the r is equal to 0. So let's actually use an example of that. And it's going to get complicated real quick. Just do an example. So we want to find the horizontal asymptote of the function. Let's see, this is going to be f of x is equal to 9x to the 6th minus x divided by x cubed plus 1. And you might already be like, what the fuck is this nonsense? How do we find the horizontal asymptotes? We can do it. So the first thing I need to clarify is what we're actually looking for. So we need to find two limits. So we need to find the limit as x goes to positive infinity of f of x, and the limit as x goes to negative infinity of f of x. Because if we're not doing both, we are only checking one side, and it could have two horizontal asymptotes, could have just one, could have none. So we need to check both. All right, so now let's do one of those limits. So the limit as x goes to infinity of f of x. It's supposed to be infinity. Hope you guys don't mind my horribly drawn infinities. They will never look good. So that's the same thing as limit as x goes to infinity. We're just going to plug in that function now. 9x to the 6th minus x divided by x cubed plus 1. All right, so what we're going to do here is we want to take something that goes to 0. If we look at this intuition right here and we keep on, like with continuous functions, we can plug in infinite. We can actually plug in the values. If we say like if we have a nice limit, as x goes to a and f is continuous, and we could say f of a. So we can kind of use this intuition a little to tell us that we need to do more. So if we look at, as x gets bigger and bigger, the top is also going to get really, really big. The bottom is also going to get really, really big. So that's not particularly helpful. So what we need to do is get something of the form like this. We need to get something of this form. And it doesn't, what we specifically need it as is like we could have it of the form 1 over x to the r. And that's pretty nice because, then this will go to 0 and that will just be 1 over 1. But the idea is we want to get something of that form. And if we look at our function here, we don't actually have that. So what we want to do to get something of that form is we want to get rid of this x cubed. So how do we do that? We would have to divide by 1 over x cubed on the bottom. So whenever we divide out, this x cubed will go away, and we'll have it on the bottom instead. But likewise, you can't just multiply things willy-nilly. So we need to do that up top as well. And also, one of the things that we need to clarify to begin with is that x cubed is also equal to... the heck? Sorry, I just got a text. Is also equal to the square root of x to the 6th. And this is because x is greater than 0. If it was positive or negative, if it was a negative limit, then we have to be more technical about it. But we keep that in mind as well. All right, so now let's actually distribute all that in. So we have the limit as x goes to infinity. And now what we're going to do is, you know what, I need to write more room. Let me give myself some more room. So now what we're going to do is move this into kind of like the radical. We're going to try to write it as like a bunch of fractions. So this will be 9x to the 6th minus x divided by square root of x to the 6th, because that's what that is. That's what the same thing as x cubed. And then what happens when we divide on the bottom is that this will be equal to 1. X over x cubed will be equal to 1. And then the other piece will just be 1 divided by x cubed. All right, so now the fact is that, both of these terms are here on the top. This is a square root, this is a square root, we can combine them. We can actually, you know, combine them. We could, you know, if you have like a squared times b squared, that's the same thing as just ab squared. Same idea with square roots. So now let's just go ahead and do that. So this will be the limit as x goes to infinity. And now it's going to be 9x to the 6th minus x divided by x to the 6th, still divided by 1 plus 1 over x cubed. Alright, I'm going to fix that square root. That looks awful. Alright. And all I did was just move it inside. And now that we have this, I'm just going to go ahead and erase it and simplify. Not simplify, but what becomes is this. Is that we can basically just, you know, break up the fraction over the subtraction over minus or whatever. And then we get that. So now let's actually simplify. So we have the limit as x goes to infinity of, so we have 9x to the 6th divided by x to the 6th, so that will just cancel. So just 9 minus, here we have x to the 1 over x to the 5th, so this will be 1 over x to the 5th divided by 1 plus 1 over x cubed. So if you remember the previous theorem we talked about, is that the limit as x goes to infinity of 1 over x to the r is equal to 0 whenever r is rational. So what we can do now is that this term will go to 0, this term will also go to 0. So what this means is that the limit will actually be equal to the square root of 9 minus 0 divided by 1 plus 0, but that'll just be equal to 3. Oops. All right. So hopefully that kind of makes sense. Is that the idea is we want to write it as these kind of fractions right here. We want to eventually, our end goal is to write it like that. And if you can do that and you kind of do the behavior of it, you know, if you keep on adding really bigger values of x, you see that eventually what's happening is that 1 over x to the 5th, 1 over x cubed will be approaching 0. So as their limits will be 0. So that's why this 0 is here and that 0 is here. All right, so it's a bit of a process, but the idea is we want to write it like that. That's our end goal. So what we have here is, so far, is that the line y equals 3 is the horizontal asymptote. So now let's do the other side. The limit as x goes to negative infinity. So I'm just going to not explain too much, but just note in this idea that we have x to the 6th, the square root of that, x cubed is equal to the negative version of that. And this is because x is less than 0. And this is a very important distinction, is that in this case, x would be negative. And if you want to test this, if this is true, let x equal like negative 1. Here, this would be equal to negative 1. If you didn't have that positive here, then this would just be negative 1 to the 6th, which is just equal to 1. And you get the square root of 1, which is equal to just 1. So you need the negative out there whenever you're working with the negative side. All right, so now let's blow through it. So limit as x goes to negative infinity of 9x to the 6th minus x divided by x cubed plus 1. Again, we're going to be multiplying by, typically what it is the highest power in the denominator. So it would be 1 over x cubed and what that's going to give us is going to be the limit as x goes to negative infinity. And again, remember in this case that x cubed will be equal to this, so it's going to be negative. So this will be negative 9x to the 6th minus x over the square root of x to the 6th. Sounds pretty wordy. All divided by 1 plus 1 over x cubed. Now I'm just going to simplify just the top because it's pretty messy. The limit as x goes to negative infinity, it's going to be negative 9x to the 6th divided by x to the 6th minus x over x to the 6th. All divided by 1 plus 1 over x cubed. And again, like as we had before, these will cancel, and this will be 1, so this will just become 1 over x to the 5th. So this will just become 9. And this right here will just become 1 over x to the 5th. So now when we take the limit, we have this goes to 0, and that this goes to 0 as well. Oops, it's not that. It's not the limit anymore. We do the negative square root of 9 minus 0 divided by 1 plus 0, which should be equal to negative 3. So we have the second horizontal asymptote, which is y is equal to negative 3, is a horizontal asymptote. All right, so this right here is a bit of algebra, and just so you know, the idea is, let me just circle it blue. The idea is that you want to get something of this kind of form at the end. You want all your x's as, fractions. You want all your x's in the denominator or something like that. And the way you do that is by you look at the highest power of this, you look at x cubed, which was x to the 5th, x to the 9th, and you would divide by that. And doing that kind of work will allow you to get rid of that. All right. So we can have other cases where, this is still not very nice. So let's just go ahead and do another example. So you want to evaluate a limit again. As we always want to do is just evaluate limits. Evaluate limit as x goes to infinity of square root of 9x squared plus x minus 3x. Again, this is not very nice. If we let, either of these things kind of go to infinity, what we get is they both go to infinity. So let me just kind of say that in words. So 9x squared plus x goes to infinity as x goes to infinity, and negative 3x goes to negative infinity as x goes to infinity. So if we just want to try to plug in the limits already, what we get is infinity minus infinity. So this is an example of another indeterminate form. Again, so this means do more work. An example of why infinity minus infinity doesn't tell you anything, you could just do, x minus x. You could do, x, negative x plus, 1/2 x. But you can easily construct an example where both of the limits of what you're actually trying to represent is equal to positive infinity, negative infinity is equal to some number. It could be whatever we need it to be. All right, now let's do some math magic or some complicated algebra. All right, so now let x go to infinity again of 9x squared plus x minus 3x. So the idea is we want to get rid of the square root and try to put it into the same kind of form we had above. Again, we want something of 1 over x cubed or 1 over x to the 5th. So let's go ahead and do that. And the way we do that is by multiplying by the conjugate again. So in this case, we'll be multiplying by 9x squared plus x plus 3x, because that's going to be like, it's just the opposite. It's the same thing, but the second term is, has like a negative sign now, or it has the opposite sign. So likewise, as we multiply it, we have to divide it by it. And we have plus 3x. So now let's actually begin to simplify. So the limit as x goes to infinity. So this will actually become 9x squared plus x minus 9x squared. So that will just be that term squared, and the other term, 3x squared, is just 9x squared. And then on the bottom, what we have is just 9x squared plus x plus 3x. So now what we need to do here is, it may not look like it, but the highest power is actually like 1. Because you might ask yourself, how do I get rid of this x? How do I get rid of that? Basically what we do is we look at the fact that this is a square root, this is a squared. So the highest power will be x squared inside the radical. And now we have a radical, so that'll just basically just be x. So in the case if it was x to the 4th, for example, then we do x to the 4th, square root of that, that's equal to x squared, so that we would need to divide by x squared. So in this case, the highest power is just x, so this will be, we need to get rid of those x's on the bottom. We'll put them in denominators on the bottom, so it'll be 1 over x times 1 over x. And now let's actually distribute. Okay, one other thing to notice is that 9x squared up here, 9x squared here, just leaves x up top. Pretty nice. All right, now let's keep on going. All right, so considering the algebra is pretty same, I'm just gonna jump a bit. So up top, what we get is just x divided by x, so this would be 1. If we try to move it inside, we get 9. Oh yeah, one other thing again. So x will equal to square root of x squared. It's positive x greater than 0. Remember, if you do this trick, you always have to remember if it's positive or negative. Here, what we have is the square root of 9x squared plus x divided by the square root of x squared plus 3. And again, because the x goes away because we're multiplying by 1 over x. All right, so now we're going to do the limit as x goes to infinity. We're just going to go ahead and just put the x squared in, and what we get is just 9 divided by x, 9 times x squared divided by x squared, which is just 9. And we get 1, you just get x divided by x squared, and you can just check this yourself because it's still like the same kind of stuff as we did above. So we get that. And now it's of the form that we like. So now we can just, do the limit. We have that 1 over x will go to 0. So what this means is that we have 1 over the square root of 9 minus 0, plus 3. And that's just equal to 1 over 6. All right. So that basically covers this kind of section right here. I mean, this little part right here. But we still have to deal with some more limits. So in this case, all the limits are equal to some nice values. Like the limits exist, but they're actually like pretty nice. But in the case that we had before, we had a function could go to infinity as x goes to infinity. So that's actually its own kind of limit. So just now it's going to be infinite limits at infinity, which sounds weird. This is still the same section, so this is why I still got to cover it. This idea is that infinite limits means the function goes to infinity. At infinity just means x goes to infinity. The notation that we use would be, say the limit as x goes to infinity of f of x is equal to infinity to indicate, as you expect, that to indicate values of x grow unbounded, or values of f of x all right, so what we say is, all right, we say, the limit as f of x as x goes to infinity is equal to infinity to indicate that f of x becomes increasingly bigger as x gets larger. I realize I need to say things before I write them. So this is basically a way of saying as x gets big, f of x also gets big. So we have the same kind of notions attached to other, like, negative infinities and positive infinities. So in this case, it'd be like the limit as x goes to infinity of f of x is equal to negative infinity. This means as x gets bigger and bigger, f of x just becomes more and more negative and basically just becomes unbounded as it goes to negative infinity. Likewise, we can do now the negative side. So it was limit as x goes to negative infinity of f of x could equal to positive infinity. So basically as x becomes, like more and more negative, as x goes to larger and larger values of negative numbers, the function will go to positive infinity. And likewise, by the last case, as x goes to negative infinity of f of x is equal to negative infinity. Again, this just means that the function, as x becomes more and more negative, f of x does the same thing. So, quick example of just some functions that we have the kind of limits would be, well, not as an example. So just see, we would want to evaluate the limit as x goes to infinity of x squared, and the limit as x goes to negative infinity of also x squared. Oops, I said x squared, but I wrote x cubed. All right. So just a quick reminder of the graph if you don't remember what that looks like. It's going to start at 0, go to infinity, and as we go to positive infinity, so this would be like positive infinity, and as we go this way to like negative infinity, the function actually increases. So what we say is, as x gets larger and larger, so does x squared. So what this means is the limit as x goes to infinity of f of x, well, not f of x, but x squared is equal to infinity. Similarly, for the negative version, as x goes to negative infinity, x squared becomes larger and larger. Thus what we have is the limit as x goes to negative infinity of x squared is also equal to infinity, well, positive infinity. All right, so that's not too bad, but let's do another example real quick. So just an example. In this case, we did x squared with both both as we approach negative infinity and positive infinity have the same limits. So let's just do x cubed real quick. So let's just say the limit as x goes to negative infinity And our goal is to evaluate that. So again, just a quick reminder of what that function looks like. Oops. Look like this. So basically, very similar to kind of like x squared, but instead of going positive, now it's going to be negative. So what we have again, so as x gets larger and larger in a negative direction, we have that, x squared will also go to not x squared, x cubed will become, a larger and larger negative value, negative number. All right, so again, what this means in terms of limits is that what we have is the limit as x goes to negative infinity of x cubed is equal to negative infinity. Basically the same kind of thing we did above, but now instead of positive infinity, it's now equal to negative infinity. All right, so now let's do another example that's kind of different. Say I want to find the limit as x goes to infinity of x cubed minus x squared. So again, we can't just, evaluate the limit separately. So note that we can't. So we can't break up the limit over the fact that it's a difference. So we get, limit of x cubed minus the limit of x goes to infinity of x squared, because they'll be equal to infinity minus infinity, which you get is indeterminate form. So again, not useful. But we can easily just do some algebra. So again, let me just clarify. This will be indeterminate. So it means more work. So let's actually do something else that's actually helpful. In this case, we could just, rewrite the inside by just taking out x squared. So this will be equal to the limit as x goes to infinity of x squared times x minus 1. So what we're going to note is that x squared goes to infinity and x minus 1 goes to infinity as x goes to infinity. So the product must as well. So what this means is that the limit as x goes to infinity of x cubed minus x squared is also equal to infinity. All right, guys. So I think that's it for this section. This stuff is a little strange to begin with. And also sorry that it might be a little bit messy today. I'm still kind of tired from writing the other one at 4 in the morning. But this stuff isn't too hard. It's just a bit weird to get used to. And the only real trick you have to know is how to do some algebra tricks. But if you I'll try to explain the best I can with those for you and what the ideas are. And if you're always unsure, feel free to shoot me an email. I'm always down to help out. But adios. Like, comment, and subscribe. Hit the bell icon, I guess. I don't know. But adios.